Okay, all. So we're going to look at the processes that go on now in this nephron. I have sort of talked about the reabsorption, but let's think of the afferent arterioles bringing blood in. This is leaky. Fluid is going to leak out. That's what we want to filter. So that filtration is going on here in the glomerulus. Okay, so boxed here, the term filtration. And as it travels along the nephron, we don't want to lose all that fluid. So some of it isn't going to end up being urine. Instead, it's going to be reabsorbed from what would have been an elimination of urine from the nephron. Instead, we're taking it back into those peritubular capillaries. Now, there's a third process called secretion, and that is, imagine that something that was floating around in the blood never did get filtered, and it kept on going through the efferent arteriole and into the peritubular capillaries, but we do need to excrete that. We need to get rid of it. So we're able to then remove it from those capillaries and put it back into the nephron in order to be eliminated. That's called secretion. So don't confuse reabsorption and secretion. They're exactly the opposite direction. One is reabsorbing to save water in the system. The other is actually eliminating. And finally, excretion, which is at the end of my nephron in the collecting duct, that fluid is going out. Okay, and that's going to be excreted. Filtration, reabsorption, secretion, and excretion. Okay, moving on. This series, couple slides will write that out for you. Filtration, fluid moves from blood to the filtrate. We're going to call it filtrate, not quite urine yet. Reabsorption is fluid moves from the filtrate back into the blood. And so one's like recycling and one's like a sieve, like filtering. And then secretion, the waste moves from the blood to the filtrate, even though it wasn't really ever filtered from the beginning. And then excretion, which is elimination from the body. That is urine, right? It was once filtrate, and now we're going to call it urine. So those are the processes. Now, where do they happen? The location in which they occur. So filtration is happening in the area of the glomerulus, right? So there's my filtration. And reabsorption is going to be happening in lots of different areas. Immediately, like 60% of it happens right away there in the proximal tubule. But there is regions in the ascending loop, descending loop, and distal convoluted, and collecting duct. So in all of those regions, you will also see reabsorption. Not as much as in the proximal tubule, however. Next is secretion. Where is it happening? Well, it happens in those peritubular capillaries close to the proximal tubule, very close to where it didn't get filtered, and then at the very end. At the distal convoluted tubule is where still circulating around some substance needs to be eliminated. A lot of times it's urea. Is going to be dumped into this region of the distal convoluted tubule or into the collecting duct itself. Excretion then is happening here at the very end. When you actually finally eliminate it, it's going to be excreted. Filtration into filtrate. Reabsorption out of filtrate. The reason I'm nailing this on you again is because students get confused into which direction what is moving. So secrete out of the blood into the filtrate. Okay, remember that we are filtering blood and manufacturing urine. Students often get that backwards. Here's the glomerulus, the Bowman's capsule, and the proximal tubule, illustrated really in a nice way. And think of glomerular filtration rate. GFR is glomerular filtration rate. In other words, how much are we really filtering here in this glomerulus? How much is really getting removed from the blood in this region? So I like this analogy. It's kind of like a soaker hose. Those leaky capillaries are like a soaker hose that you would have in your garden, or a garden hose that has all the holes in it, and then when you just lay it among your tomatoes, and then when you put the faucet on, it just sort of slowly leaks out through the holes. That's kind of what is going on here in these capillaries in the glomerulus. So what are the forces that contribute to that rate of that filtration in the glomerulus called GFR, glomerular filtration rate? Well, the first thing is how much pressure is in that capillaries, correct? Think of the hose again. If you have very little pressure coming into that hose, very little of it is going to leak out. So blood pressure. So if the blood pressure is high, you're going to be filtering quite a bit of this blood in order to make urine. Colloid osmotic pressure is an opposing pressure. So if this hose has holes in it, things are going to want to go out, but things are also going to want to come in. And so if there is a lot of osmotic pressure trying to come into the hose, then that's going to be the osmotic pressure. And I'll show you more pictures of that if it's not quite clear yet. And then the fluid pressure in the Bowman's capsule. That's in the balloon itself. If the balloon fills up with too much of that fluid, it creates a lot of pressure, also wanting to come back in through the little hole that it went out. Correct? So one is hydraulic, meaning how much of that pressure leaves the hose, and the other two are how much is coming back into the hose. So if blood pressure is around 55 millimeters of mercury, let's say, and the osmotic pressure, osmotic is because, look, think of, this blood pressure is making it filter out, but there is also lots of solutes here and a lot of solutes here, and this is water is going to want to move in towards where there's the highest solute concentration. So it's an osmotic pressure wanting things to come back in through the little hole that they went out. And then the fluid pressure, because if I put too much water in this area here, then it's going to definitely form enough pressure to want to go back in. This is hypothetical numbers, but they are real. You can have a blood pressure, of about 55, and two opposing pressures that added up are about 45. So anywhere between 40 and 45, there is the opposing pressure, and you end up with a net filtration pressure, which is mostly out, even though you had a force trying to come in, another force trying to come back in, that the net filtration pressure is in this direction, the biggest one of the blood pressure direction. Take a quick look at these diagrams, right? Blood pressure, osmotic pressure, fluid pressure, total net filtration. Just illustrated in a different way. Afferent arterial, efferent arterial, blood trying to move fluid out, and the two forces that are trying to move fluid back in again. This is written out for you so that you can study it. Pressure responsible for pushing fluid out of the capillary and into the kidney tubule is the blood pressure. And so it gets us thinking about, well, what if blood pressure, it changes through the day, right? You have a little higher, a little lower. Does it mean that your filtration rate at the level of the kidney is going to change along with it? In other words, is there times of the day that you make more urine and other times that you make less urine? And how does that work? Well, adrenaline is going to make blood pressure change, correct? Exercise is going to make blood pressure change. So again, I throw that question at you. Does filtration in the kidney vary along with this? And the answer is no. You would think it would, right? But the answer is no. So GFR is constant. It's constant if the mean arterial pressure, in other words, the mean pressure of this individual, this patient, is anywhere between 80 and 180 millimeters of mercury. That is a gigantic range. It's got to be super, super low and super, super high for GFR to actually change. So most of the time, even with quite a bit of fluctuation in blood pressure, there will be no change. So this is regulated. This is homeostasis. You don't want to be making more urine just because you ran around the corner. So value is quite constant. Now there are some extreme conditions, right? If blood pressure is way too low or way too high, the GFR changes so that your information can compensate. So if your blood pressure is really, really, really low, right, then you're going to want to conserve as much fluid and not urinate it out, because if not, your blood pressure is going to drop even lower. So it's a compensatory mechanism. And then if your blood pressure is way too high, then it would make sense to make more urine and try and bring that volume down a little bit. But it's only in extreme conditions. Now, along in this system, there's also the effect of hormones. And we're going to talk about two. ADH, which is also called vasopressin, or ADH is anti-diuretic hormone. Anti-diuretic, meaning reduce the amount of urine that you make, right, or eliminate. And also aldosterone. I think I'm going to skip this slide, guys. Let me skip this. And let's talk of control of sodium balance. So what happens when you eat lots of salty Fritos? Okay, you ate all this salt, and it's going to trigger thirst, right? You get really thirsty. And so you get very thirsty, and you've gotten so much salt in the system that you need to have lots of water to dilute it. And if you're not drinking it, then you better not urinate it out, the amount that you had already. So you're going to save water. So the result here that I'm telling you is conserve water, and in that way increase the blood pressure. Next, to rid body of extra salt and extra water. So next, what you're going to have to do is get rid of all that salt that you just ate. Do you notice? So anti-diuretic, you're going to release it when you don't want to lose more water and you haven't yet regulated that sodium, that NaCl that you ate too much of with your Fritos. So how does it do that? How does ADH, or vasopressin, regulate that? Well, it does it by changing the permeability of the collecting duct. Remember where that was? To water. So the collecting duct has a certain permeability, and you're going to alter that, and it's released in response to high blood osmotic pressure, right? You just ate a bunch of salt. So the blood osmotic pressure just went up. So imagine here, vasopressin makes collecting ducts more permeable to water, right? So this is my collecting duct, and the osmolarity is high because you ate all the salt. So whereas we ordinarily would have kept this water and you would have urinated it out, what happens now is it altered the permeability of the collecting duct, meaning it made it more permeable and water escapes. If water escapes, it goes back into the blood and you fail to urinate it out. So you ate your Fritos, you release ADH, you reabsorb more of that water, do not urinate it out. This happens with something amazing that's called aquaporins, and they're water channels. And this Peter Agri won the Nobel Prize in 2003 for his work on aquaporins, which he figured out was an insertion in the membrane of a little channel that was a water channel. And that had never been seen before, that you could have a channel that was not for ions, but specifically for water. Yay, aquaporins. And we have lots of those in the kidney. Let's stop now and continue on the next video. Bye.